Good afternoon, all. We'll start our session. In the previous session, we have discussed about error detection and correction, where we have discussed several categories of errors that we can identify in the network, like single bit error, burst errors. Burst errors are nothing but more than one bit of error if it is applied or if it is occurred, then we call it as a burst error. So, with respect to that error detection technique, we have seen one technique that is by the name called as block code. What is this block code is all about? Whenever you just transmit a bit, it will not be transmitted one bit at a time with respect to the transmission channel. So what it will be doing is it will be just analyzing how many bits of code you can just combine and you can just transmit it. So the block is nothing but more than one bit you can transmit it, like 4 bit, 8 bit, 16 bit, 32 bit, 64 bit, like that. Some blocks will be just maintained. So with respect to that blocks, we are just transmitting it. How to detect the errors? We have identified one method to detect the errors with respect to it. So what we'll be doing in the block code is we'll be just analyzing, we'll be just taking care about um, the data about whatever is transmitted. I'll just add one redundancy bit to that particular data bit or the data that I need to transmit. One or more than one redundancy bit, depending on the standard notification, we'll just add it. If that is added, then we'll just take care about transmitting it to the next one. We'll not transmit the exact data, we'll add some redundancy bits so that it can be easy for us to detect the errors. So here the redundancy bit that we are adding is nothing but a parity bit. So that's what we have just added, and we have just transferred to the next particular block. We can just take care about the previous slide, whatever we have just discussed with respect to that. So whatever the changes or whatever the modification that we'll be just having it with respect to your two code words that has been available. With respect to that, it will be just taken care. What it will be doing, see, best thing that I can just explain you here is, I'll just try to annotate it. I'll just try to give you the answer for it. See, how your distance, Hamming distance will be working, right? It will be difference between the two code words. So code word with respect to that. So what I'll do is, I'll just have a data word, for example, 0, 0. Okay, so 2 bits at a time, I'm just transmitting it. For that, I need to just have a table, right? So the table containing all the possible values. Okay, so 0, 0, 0, 1, 1, 0, 1, 1, right? So this is what it will be having. So now if you just convert it to a code word, so I am going with even parity checking. So with respect to that, I'm adding one more redundancy bit along with 0, 0. I'll add one more particular bit. What is the particular bit? It is an even parity checker. So with respect to that, 0 is an even number. So that's why 0 will be the bit that will be added over there. Similarly, with respect to your second bit, second data block. Second data block is 0, 1. So 0 followed by 1 will be transmitted, right? So that's what it is. So with respect to this, it is an odd number of ones is there. In order to make it as an even parity, you need to add one extra bit. That extra bit should be 1. It should be transmitted as 1. So similarly, it goes on. The next part is 1 followed by 0 is the data word. With respect to this, it's also containing odd number of ones. So in order to make it as even number of ones, parity bit should be high. So the last one is even number of ones is that. So no problem at all. So you can just make it as low as the last bit. That is 0. So this is how it will be working with respect to your parity checker, right? So with respect to this, now code word is available. Now what they are saying is, with respect to this particular code word, whatever the distance you are calculating it, how many bit of changes that you can just make it? How many bit of changes that you can make it? So that is nothing but your minimum distance. See, in each of these particular cases, whatever the values that you are having it, in each of these particular cases, you will be always getting the answer as minimum distance. The minimum distance will be equal to 2, because minimum distance, instead of it, what I'll do is I'll just try to calculate the distance between the code words or changes that you can make it. So max the changes that you will be doing is 2 itself. So that's what it will be having. So 2 errors at a time. You just 2 different type of errors. You can just or one type of error you can just have it with respect to your any of the particular block that you are having it. So distance will be 2 means what it will be doing is it will be saying that 1 bit will be used for detecting the errors. And remaining one bit is used for correct. This may be the possible value that you will be having. How to detect this? See, whenever you are just having this particular scenario, you need to think of a matrix type. So how this particular matrix works now in the similar fashion. Suppose 0, 0, 0 is my first block. Similarly, 0, 1, 1 will be the second block. Third block is 1, 0, 1 will be the third block. And similarly your last block is 1, 1, 0. As you have identified the parity bit with respect to your rows, you need to identify the same thing with respect to your columns also. Zero, zero, zero. Similarly, 0 followed by 1 followed by 1. Similarly, 1 followed by 0 followed by 1. Similarly, 1 followed by 1 followed by 0. Okay, so this is the parity bit. That's what we have just analyzed it, right? So what I'll do is I'll just try to write the other one also. Then it will be easy for us to work. So with respect to your columns, if you are just changing it means 0, 0, 1, 1 will be there, right? 1, 1 will be even number. Similarly, with respect to the next one, it will be 1, 1, it will be 0 itself. Why it is 0? Because it is taking care with respect to 1. Similarly, 1, 1 is done, 0 will be the one. So this is nothing but your parity checker. So now with respect to your Hamming distance, whatever the changes that you will be just doing it, if you change it one particular n number of bits, you can change it, right? So like that, 2 bits or that means 2 bits you can just change it, or more than one. Why more than one? Because of this particular correction. So this is how it will be working with respect to your Hamming distance calculation. Okay, so the minimum distance, how why it is s plus 1? Because it will be nothing but it can detect up to yes number of errors, but not guaranteed. So that's what the meaning that it will be saying with respect to your d minimum calculation. This Hamming distance is nothing but the changes that you will be having with respect to the keywords. That's it, or the code words. It has been sent as well as it has been received. So difference between that, if it is 0, then it is accepted. If it is more than 0, then it will be discarded. So this is what it will be having. So this gives you a clear picture of how your d min will be calculated. See, with respect to your detection, it will be detected at the receiver itself. So from the sender only, it may be corrupted and it can be transmitted to the transmission medium. The transmission medium, while traveling, whatever the distance that, whatever the radius that it will be having to get this particular scenario, so it will be always the minimum. That is the distance, the minimum distance, or the changes will be always reflected to more than yes number of errors. That's what the meaning with respect to detection. Correction, if you are just going with it, then one more territory you need to just analyze. It is same number of errors may be fed with respect to your other territory also at the receiver. So the combination of it works. So d minimum will always be greater than 2 times of t. That's how you need to just analyze it. 2 times of t, whatever it will be there. So if you are just guaranteeing, if you are calculating the Hamming distance with respect to your block code, always d minimum will be equal to 2 times of t plus 1. That is greater than, right? Greater than or equal to 2t plus 1. It will be there. So as it is with respect to your correction, detection, similar thing with respect to your correction also. While correcting it, 2 times of that particular number of errors that has been implemented. Why? Because of the 2 territories that you are having. Okay. So with respect to this particular example, we have d minimum is equal to 4. See, remember one thing, whenever you have an even number, then it is always you will be getting one bit of minus 1 with respect to the uh, distance that has been given, whatever the dmin. Dmin is nothing but minimum distance that is there with respect to calculating the differences that we'll be having with respect to your code words, right? So that is what, if the distance is 4 among themselves, among the code word, if the distance is 4 months, then your error detection and correction method, sorry, if it is an even number, just go with this particular type, even number, then it can detect one less than the distance value of errors and correct one bit error. Whereas if d minimum is an odd number, then it can detect n errors and correct it also. So this one we need to remember. According to our example that has been given, d minimum is equal to 4. With respect to this, if I just split it one bit at a time, so I need to take care with respect to your so 3 plus 1. So 3 errors I can detect it. 3 errors can be detected and 1 error can be corrected. So respect to our given scenario. So if you are always keep remember, so your distance should be at odd number, then you can detect n number of errors and correct it also. Whereas if the d minimum is even number, then it can detect one less than that particular number, will gives you the number of errors that it can detect. It can detect, but it can correct only one bit of error. Okay, if it is detected, then one bit of error can be corrected. That's what it is. So that's what the meaning of it. Next one is linear blocks. Linear block code. What is this linear block code? Once again, we need to annotate this because we don't know what is happening over there, right? So for better understanding, we'll just take care how this thing works. Yeah. Okay. Suppose we say that we have a data word, because we'll take the two particular block code itself. 2-bit block code only we are just sending it. So with respect to this, what will be the resultant code word? Yeah, we know that. Once again, I'm just writing it. 0, 1 is there means it's an odd number of ones is there. So in order to make it as even, what need to be done? So 0, 1 followed by one more bit. The parity bit should be 1 itself, right? Yeah. Similarly, we'll just go with the next one. So it is 1, 0. Yeah, it will be 1 followed by 0 followed by, right? The next one, uh, 1 followed by 1 with respect to this. This is This is 1 followed by 1 followed by 1. Okay, so this is the data word followed by the code word. This is how it will be, right? So now what your linear block code will be saying is, if you XOR between the valid code words that you are having, say for example, the valid code word is 0 0 0, and the another valid code word is second code word, I'll just say it 0 1 followed by 1, right? So if you XOR, if you perform the XOR operation among this, whatever the resultant value that you are getting at, it should be a valid code word. If that is the case, then we call it as a linear block codes. Understanding it? So this is with respect to 0 0 0. We'll take the other example. So for your 0 1 1, if I just take it as a bit representation, so this is the first code word, and the second code word I'll take it as 1 0 1. Okay, so now whatever the resultant code word, you need to apply the XOR operation. Once again, I'm reminding you, you need to apply the XOR operation among these two particular code words. So 1 will be the value. After that, 1 will be there. The last bit will be, least significant bit will be 0. Why? 1 1 0. 1 0 is 1, 0 1 is 1. So if there is any change in the bit, then it will be high. But if there is no change in the bit, both are one and the same ones, it will be low. So that's what we have just analyzed. So based on that, we have just cultivated the habit of doing this. So this is nothing but your valid. This is whatever the thing that you are checking it. Okay, you got the answer as 0 1 1 with respect to your after performing the XOR operation between the two code words that you have having it. Two code words. I'm not talking about the data words. I'm talking about the code words. So 0 0 0 0 1 1 will result in the 0 1 1, which is a valid one. It is available here. Similarly, 0 1 1 with respect to 1 0 1, it will be resulting the values. Oh, sorry. Yeah, I need to just try to write it once again because I have written it one way, one in one area. I have just made it wrong. So 0 0, if it is having means the code word will be 0 0 0. Okay. So second one is 0 followed by 1. So similarly, with respect to this, the value will be 0 followed by 1 followed by 1. Okay. The next one will be 1 0. That is what the combination that we need to just go with it. So with respect to this scenario, so it will be 1 followed by 0 followed by 1. Okay. The last one is 1 followed by 1. So with respect to this, 1 1, it will be 0. Okay. So with respect to this now, what is the linear code word is? So we need to take the two valid code words which is already available. So among those two, I need to perform the XOR operation. That's what we have just analyzed. We'll just take first the code word and the second code word. So with respect to that, if you just apply the XOR operation, then the resultant will be 0 1 1, so which is a valid code word. Similarly, if you just take the example of one more code word, say for example, I'll take second code word, that is 0 1 1. That is what the second code word is. So with respect to that second code word, the third code word I'll just identify. It is 1 followed by 0 followed by 1. Okay. So if you just apply the XOR operation for this, so the resultant will be 1 followed by 1 followed by 0. So the resultant, whatever you are getting it, is nothing but one more valid key. So that's why whenever you just apply or you just perform the XOR operation between the valid code words, the resultant code word should also be a valid code word. The resultant code word is the one which will be just transmitting it. That is nothing but your linear block codes. So in that particular manner, you need to choose the thing. So the minimum distance, we will be calculating it accordingly. Okay. So there is no much change with respect to your block codes and linear block codes. Only differences with respect to the valid code word, you will be applying the XOR operation. The resultant one will be always a valid code word itself. That valid code word, I'll just set it. I'll not change any other thing. So same example that we have taken it. So same thing has been listed here in the table format. You can just perform. You can just go through it. So quickly, we'll just move on to the next one. In the linear block code, the minimum Hamming distance is the number of ones in this non-zero valid code word with the smallest number of ones. So what is the minimum distance that you will be calculating with respect to your linear block code? See, simple. It's very simple as okay. What I'll do is just try to annotate it if possible. Yeah. Once again, the same thing. So if I take this example, it is 0, 0, 0. So it will be three zeros. 0 followed by 1. If I just take the data word, then 0 followed by 1 followed by 1 will be the answer, right? Why it is even parity should be maintained. So just because of it, one bit will be added for it. So 1 followed by 0, same thing. It will be 1, 0, 1. Similarly, 1 followed by 1. It will be, so even parity is that. So no need to make this particular parity bit as high. So it can be kept as low. So this is what the thing that we are having. So you need to identify the non-zero valid code words. Non-zero valid code words are 0, 1, 1, 1, 0, 1, 1, 1, 0, right? These three are valid, but it is not containing it. It will not, it is not the zero code word. So this is a non-zero valid code word. So in this, how many number of ones are there? Which is the smallest number of ones? That is nothing but your minimum distance. See, in all these particular cases, the minimum will always be written like that as 2 itself. So that's why 2 is the minimum distance that you will be carrying in this category. Minimum number of ones wherever you are just having it, that is nothing but your minimum distance. Understanding it? So that is the thing that you need to just analyze. Why? In our first code, whatever the thing is that the number of ones, non-zeros that you are adding it 2 to 2, that will be the minimum distance. The number of smallest number. If suppose if you have, suppose I'm not saying that it is that. Suppose if you have 1, 1, 1 also with respect to that 1, 1, 1, then the minimum distance will be retained as 2 itself, because 2 is the minimum number of ones, smallest number of ones that is occurring in the valid code word. So that's why non-zero valid code word. So that's why it will be 2 itself. So that's how it will be just working. Next one, we'll just jump into in this particular linear block code. One simple linear block code that we are just seeing it here is simple parity checker. What is a simple parity checker is all about? Simple parity checker, what it will be doing is, see, with respect to our previous example, itself, you just try to analyze that. So if we have a table like 0, 0, the code word will be 0, 0, 0. You're adding one bit. So the next one is 0, 1 is there. Then you'll be adding the bit as 0, 1, 1. One extra bit you are adding it to the data word. So your K represents number of bits that is available in the data word. And N represents number of bits that is available with respect to your yeah. N represents number of bits available in the code word. So this is how it will be working with respect to a simple parity checker. So it will be 1, 1, 0. What the changes that we can just make with respect to that. So N always represents number of bits available, number of bits in the code word. Code word number of bits, if you want to just have it once, then go with the N. K is nothing but always it will be representing number of bits in data word. Data word is what we require. Code word is what we just generated. So keep that in your head. In the simple parity check, your D minimum will always be equal to 2. So 2 bits changes, you'll be always getting it in the linear block code whenever it is a parity checker, simple parity checker. So it will be exactly equal to that. So you need to just remember this. Okay. So keeping this in our head, we'll just move to the next one. So the next one is very simple parity checker code. Here they are taken 4 bit at a time. So 1 bit they'll be reserving for getting the parity generate. how the parity will be generated. It can be generated in two ways. Looking into the particular value only, you can just go with it, or else XOR each one of the operation, you'll be getting the end result. Say, with respect to this particular example, we'll just take this particular block diagram and we can just come across this. Okay, so this block diagram is nothing but it will be just giving you an idea of encoder and decoder for simple parity check code. What is the simple parity check? So we are very much sure that we are not going to send the entire data word as it is. We need to change it and we need to send it. So for the changes, whatever we are making it, so for that we require encoder that is at the sender. And in whatever the changes that has been made, it need to be discarding those changes and it need to extract only the data. But for that, we'll be using the block called as decoder. Encoder is nothing but it will be just packing it to one more resultant word and it will be just generating to the other end. It will be transmitting to the other end. Whereas with respect to your receiver, it will collect the particular word and it will be unwrapping all those particular unwanted details and only the details whichever is required, it will be just taking care. For that, we'll be just going with decoder. In the encoder, there is a one particular terminology called as generator. The data word will be first fed to the generator. What is this generator is all about? In the generator, it will be performing a simple task. It will be performing the XOR operation. That's it, nothing else. So suppose if I just take it as a data word as somewhat 1 followed by 0 followed by 0 followed by 0. If this is the data word, then in your generator, that is with respect to your R naught, we are just mentioning it, that will be equal to 1. With respect to that, each bit will be XORed. So I'll just take it with respect to your most significant bit. So 1 will be XORed with 0. Whatever the resultant value will be that one will be XORed once again with the next bit. The next bit is 0. So 2 bits are taken at the first time. So these two are over now. So after this third one will be taken into consideration. Once that is there, so you'll be just getting one more particular value resultant. This value will need to XOR with the remaining bit that we are having. So the value will be 1. So this is nothing but R naught. So now my code word will be so data word plus the resultant or the redundant word data, the generated bit that we are just done it with respect to the data word. So 1 0 0 followed by 0 followed by the last bit will be 1. Now this will be transmitted to the using the unreliable transmitter. Once it receives at the receiver end, it will receive the data bits 1 0 0 0 1, right? So same bits it will be received. What the receiver will be doing is very simple thing. It will just try to calculate once again the same particular scenario in the reverse order. So it will be having the notation as S naught. S naught will be equal to most significant bit only you try it, no problem. 1 XOR with the next bit. So whatever the resultant value will be there, so that resultant value, you just push it to the next one. So next bit you take it. Next bit is XOR with respect to which one? This is XOR. Similarly, with respect to your XOR with respect to the next bit is 0. So with respect to this, whatever the resultant value will be there, you need to just write. Similarly, the same resultant value, whatever is that will be XORed with which one? The next bit. Next bit is also 0. So with respect to this, whatever the value that you are getting is 1 itself. So the last bit that you are just transmitting it now. So with respect to that, that is Q naught here, according to this particular scenario. In this block, it is called as Q naught. So XORed with 1 once will be always resulting is 0. Once S naught is 0, once here S naught is equal to 0, accept it. Accept it. If S naught is other than 0, S naught is anything other than 0, then you just discard that. This is how it will be working. Fine. This is the generator and checker principle. So in this particular manner, we'll just take care about parity, simple parity check checks. Yeah. A simple parity check code can detect an odd number of errors. So this is what the statement that has been given over there. So what it says is, whenever you are going with simple parity check code, it can detect only odd number of errors. Odd number of errors means odd places. Wherever the odd in the odd places, wherever the number of errors is appearing, then it can easily identify. For making to understand the statement better, what we'll do is we'll just take a two-dimensional parity check code. In this, there are 4 blocks of code that is available. In each block, we'll identify the parity row-wise as well as column-wise, and we'll just have it in our particular column, respective columns. Next, what I'll do is I'll just change one bit at a time. Say suppose one bit is changed. So this one bit, it is easy for me to identify. It has been changed with respect to the second row as well as with respect to the third column. So it is easy for me to detect the error. Whereas with respect to your 2 errors, if you committed in the same particular row, it will be affecting 2 different particular parties with respect to it. One is column 3 as well as column 4. It will be highly impossible for me to detect this particular type of errors. So if it is an odd number, it is easy for me to detect. Whereas if it is an even number, then it will be far difficult for me to identify which particular bit I need to change. If I change one bit, then it will be affecting the other one also. See, if I change it, because one bit at a time, I can just change it. That's what they have given it. With respect to this, if I make it as 0 instead of 1, so then what happens? If I make it as 1 with respect to your 0, what happens? So all these particular questions will be there with respect to your two-dimensional parity check. So if it is an even number, it is far difficult for us to identify. Otherwise, with respect to your odd number, it will be easy for me to identify. Okay, so third error, so it will be affecting 3 different rows, whereas one column will be affected. So with respect to that, it is easy for me to detect it. Whereas 4 errors, it is highly impossible to detect it. So whenever you are having a two-dimensional parity check, it can detect up to 3-bit errors and correct 1-bit error at a time. Only 1 bit can be corrected, not more than that. If you correct 1 bit, then that will be the answer for it. So you can detect 3-bit errors, but it can correct only 1-bit error. That is what it will be saying with respect to your two-dimensional parity. With respect to your error correction code, we'll just check this in the next class probably. Or else we'll just try to analyze it. We'll try to analyze this. We'll just take 2 more minutes. I'll just try to analyze it. No, we'll just continue in the next class itself. Thank you very much for your patience listening. The rest of it will be continued after in tomorrow's class. Okay.